Hello, Michael and everyone. You are always so kind. I don't think that today I'm going to present any of your favorite experiments because, as we know, I tend to make things more complicated than sometimes they should be. So what I'm going to present is a quake alarm, which basically can start with only an inertial switch, and I will show you at once what I mean. For example, a quake alarm is a device that detects primary waves, which tend to move the ground horizontally, and they are almost twice as fast as the upcoming secondary waves. So by detecting primary waves might give us a time window that will allow our students to find protection under their desks and not panic. Basically, this is just have 2 eye hooks. Of course, this project progresses, as you will see. I have 2 eye hooks, one and second, and they are connected with wires. So this is just a switch that you can connect it to a battery and a buzzer or an LED, and so you can only do this. This very long screw and this plastic ball provide the switch. For example, when it touches the second eye hook, it is always in contact with the top eye hook, and when it touches the second, it gives a signal. Of course, I have used some electronics, and everything is available for anyone that wants to replicate the circuit. It's pretty much very simple. Yeah, I can send the pictures and the code. It's only 2 lines of code, and I will connect it now. I will power it from my computer USB and see what happens if well, it starts. Okay. As you can see, the code is uploaded. No, it actually starts. I don't need to upload any code at this point because it has already been uploaded. But the device waits for a pulse. I will use this rubber hammer and to provide a short pulse like primary waves will do. So if I do this, there's a red light. Red light means go under your desks. And green light, of course, now I have timed it in a certain way. It's something like a few seconds after the red light goes off. Then green light says you can just exit because we assume that there will be no aftershocks. Of course, this has to be proved, but anyway, this is the concept. So to make this, you only need 2 eye hooks, something to put them, and a long screw and something heavy, and then you just connect a circuit with a battery, any battery, and the buzzer. It can be only a 9-volt battery and the buzzer. Buzzers usually work at this range from 6 volts to 12 volts, so that will be fine. But this was our first prototype, and then we decided to go. My students, I have an excellent girls team, and actually one of the girls is sitting next to me because it's Saturday, and they always visit my laboratory on their day of school and do a few things. I will disconnect this and show you the basic circuit of another way to detect primary waves, which uses a DC motor. So I have connected a DC motor. Of course, it doesn't matter which wire goes to which terminal. And this is a pendulum, a 3D printed pendulum, which is almost, I think, 22 centimeters, which so it gives a resonant frequency of almost 1 hertz. And the reason is that the most catastrophic earthquakes in the area, like the one last September, I mean September 2021, that had a magnitude of 6 in Richter scale and claimed at least 1 life near Heraklion, Crete, and destroyed the schools. So we had a lot of work to do there, a lot of intervention with the students who were very afraid. So this is just a DC model that will produce a tiny pulse, which has to be amplified. And but if we don't want to amplify this and just see what happens if we have a vibration like this, we can just use an oscilloscope, and everything is in the form of negative and positive pulses, depending on how this pendulum moves. Of course, if you see such a movement, then the earthquake is probably very strong. You actually record a voltage, and you feel no vibration all the time if you connect it to an oscilloscope, or the DC motor will act as a small generator. And the final project, which was presented for Code League, European for Science on Stage Europe, Code League competition, was okay, maybe it's a little bit intimidating, but remember that it didn't, it was not constructed in 1 day. It needed at least 6 months of intense labor from the girls. And I will explain, of course, there's a lot of wiring, but basically it is very simple. Of course, when I present this, I say, I'm joking by saying that it is not as simple as it looks. It has, there is some art in the form of pixel art. So instead of only 2 LEDs for alt, that means go under your desk, and go, that means evacuate. We made, the girls made this. And then, of course, there is an LCD screen which shows what is happening in terms of the code, a buzzer, which unfortunately, whatever we did cannot be silenced unless we disconnect it. 4 pendulums for north to south, west west to east, and the directions between. So even if I move it like this, or if I move like this, or maybe always there will be at least one of the pendulums that will provide a very strong signal. And we combine all the signals, we feed them to a microcontroller, which is over here. The rest is just power supplies and relays. They don't make you can just not have them. And this is the circuit with, although the girls were only 13 to 15 years old when they made this project, and they won third prize. I wanted them to know about basic electronics, how we use transistors or as switches or amplifiers, and how we use operational amplifiers like this, and to amplify a very tiny electrical signal. Of course, the final device used even artificial intelligence to determine what is the right time to start the evacuation. Artificial intelligence was in the form of fuzzy logic, and this is not something very difficult. I mean, it's only a couple of functions, a couple of equations, and how they are solved depending on the conditions of the earthquake. I don't think, I don't know if you need this to see this in the full operation, because now it will be very sensitive, but we can do this. And this will be the last thing. So, of course, the aim of this project was to teach my students a lot of things that they will not come across during the Greek curriculum, and to acquire basic, well, not basic, to acquire skills like soldering, like creating electrical circuits, etc. If I start, you can see the okay, the LCD goes on and shows what happens inside this equipment. Now it's too sensitive to, and we don't have time for this. So first is it goes. This should be, when it detects an earthquake, it is like this, Alt. That means go under your desks. And then when it detects secondary waves, it knows the magnitude of, because of the intensity of the electrical signal. And then from the time from the arrival of primary to the time of the arrival of secondary, it knows the distance. For example, for 70 kilometers from the epicenter of the earthquake, it is almost a 5 seconds time window. So we know if it's distant, we know if the earthquake is strong, and we know the condition of our building. So we use a module of fuzzy logic to take the responsibility of the teacher hands. So the teacher doesn't have to worry if it's okay to tell the students to leave the room. And there are multiple sensors, like one that counts entries and exits from the classroom all day. So, and also some sensors that detect moving heat sources. So if the device will know if there are students inside, and if somebody has been, for example, under the desk and cannot move and is not detected, the device will always know entries and exits. So it will keep sounding an alarm waiting for one of the teachers in charge to check if everything is okay in the classroom. Well, this is enough. I think if somebody wants to make any of these circuits, even this one, it's not like it looks. I can give detailed instructions, and we can do it together step by step. and for sure for the first models, for the first prototypes. Well, that's all. Thank you for having me here today, and I hope we see each other again soon.
Oh yes, I hope so too, and thank you, Astrinos. They really loved it. And there was a question. I think I answered, but I want to check that I got the answer right. So they were asking if you came up with the design yourself rather than copying something you found on YouTube or something like that. And I said, I think you came up with all the plan and you coached and guided students to make it, right?
Yes, yes. Of course, I would never try to reinvent the wheel here, but I don't think that something, well, for this, for example, you can find it even as a ready-made device with a 9-volt battery and this switch, nothing more. But from this to go to the idea of using motors, it was something that just crossed our mind, because you can do it with an accelerometer, and this would be very cheap. Only an accelerometer, microcontroller, and nothing more. We use an accelerometer to as a dual input to know for sure that there was a signal, but accelerometers tend to have a lot of electronic noise compared to this set of pendulums who do not produce any significant noise, and we can always change the sensitivity. I mean, change the sensitivity in the circuit by changing the ratio of 2 resistors. So the students, the 2 girls had to do a lot of research work to know if this device works for some earthquakes, and we tested it in a vibration table as well.
It's really wonderful. Thank you. And oh, to explain what Astrinos does right now, he's in charge of the first ECFE center in Heraklion. And ECFE centers, and Astrinos can either take over or correct me if I get it wrong, but there's centers, regional centers throughout Greece, where there's a teacher who's chosen to be in charge for a 3-year period. And their job, one of the main things they do is come up with hands-on experiments that can be done in schools, provide professional development for teachers. And I don't know if, Astrinos, if you're required to have students, or if you just do that because you love what you do and you're a very giving person. Do the other ECFEs welcome students as much as you do?
Well, I think they do. It's not something that we have to do. I mean, this is a secondary education facility which aims to support secondary school teachers. But of course, we welcome primary school teachers and provide good practices or give them ideas or lend them equipment to perform the experiments in their classroom, because not all of the schools are well equipped. And at least on Crete, we welcome primary schools. Before COVID, I had 2 or 3 schools every week, and this was the best part of it, because otherwise almost nobody's interested. I am in charge of 260 science teachers of the region, and only 5 or 6 visit me regularly.
Sounds like France or perhaps some of Serbia. So thank you again. And this concludes the international presentation. So let's again thank all of the presenters who've stayed on so we can thank them.